Hey, Max. Can you hear me?
Hello.
Let me turn the volume
Uh,
up. Here, try that. Say that again.
can you hear me?
Yeah. Oh, yeah, I can hear you good. Yeah, thanks. I had to
Good.
turn.
Okay. Cool.
Um,
I'm sorry.
yeah.
Let's see.
We'll find it from last.
Oh yeah, you just need to enable screen share.
Good point.
I don't know why it does that, but yeah. Anyway.
Yeah. All right. Good point. All right. So you're going to share, and then what time is it anyway? We have a couple minutes.
Yeah.
Oh, I have to enable screen share for you.
Yeah.
Okay. Yes. So you moved to the new place, huh?
Yeah. I'm in Utah at the moment. Yeah.
I mean, your company moved to a new facility.
Ah, yeah. We're in a new facility now. Yeah. We've got like 36,000 square feet. Half of it's empty at the moment. So, um,
Yeah, you need some
yeah.
posters, like
Sorry.
posters in your office.
Yeah. And this is just a spare office now. This is the production office. Just behind this wall here is the production facility, pilot scale facility, and then all the bays at the back. So, but yeah, I'm in a shared office, so I just thought, well, there's another meeting happening,
Yeah,
so I'm in here for now. But yeah. How are you?
good. Yeah, doing okay.
Yeah, good. Yeah, they're making a lot of silicon here. We've just set up this new furnace in the pilot scale. That's what I've been doing this morning. I had to put this massive tube into the furnace, weighs like, I don't know, 200 kilos. So
So you're in what? You're not in Salt Lake City, right?
no, we're down in the south, we're in Provo.
Oh, okay. That's
Yeah,
pretty.
yeah. Uh,
Yeah. Anyway, so yeah, we can get started, I
just
guess.
started, yeah.
Yeah. So wait, let me. So Max is. I know Max from Sheffield, England. He was a grad student there. Was someone I was working with. Siddharth Patwardhan's a professor there in chemical engineering. Anyway, they're doing battery. They're doing anode for lithium-ion batteries, like replacing the graphite with silicon. And then in order to do that, because the silicon swells so much, so you need nanoparticle silicon, which is hard to get. So basically, they start with silica, SiO2, and they reduce it with magnesium. So magnesium has a better affinity for oxygen, so it can pull out the oxygen from silicon and so you can make nanosilica pretty easily.
Yeah, that's right.
To silicon, then you can get the electrodes, then pack it in, things like that. So he did that there, and then he also spent some time in Dalhousie, Halifax. That's where the Tesla battery center is, and he kind of did more of the reduction stuff for silica there.
Yeah.
We've gone from there to this company, Ionic Materials. They have mines or something of lithium there? Is that why they're?
They mine clay actually, silica clay. It's like a tubular nanotube structure clay, and they use that we reduce that into silicon.
Oh, I see.
But
So
it's because it's a tubular structure. You retain that structure when you reduce it. So you have this tubular silicon, so it's nanotube silicon at the end, which you use for batteries.
oh, is it like a biosource, like a
Oh
fossil?
no, this is natural. This is halloysite. So it's kaolin clay that's rolled up over time, rolled up into tubes
I see.
because of the pressure and the temperature and the time.
Right.
Yeah, yeah.
Anyway, so there's a lot of kind of competing people in the lithium-ion battery stuff, right? I mean, it's like
Yeah, there's a huge market. I mean, there's plenty of competition for silicon, and if you look for silicon lithium-ion battery companies, you'll find a lot of them. But then there's so much, the market is so big, so there's so much demand for silicon that at the moment there isn't really much of a competition.
uh-huh.
Yeah, so it's a good place to be at the moment. Everyone's rushing to get there first, to get to the, the first kind of, to be the first ones to produce silicon at the megaton scale. Well, not the megaton, the ton scale, metric ton scale. But yeah, there are a lot of ways to make it, and people are struggling.
How much more power, or what percent better will they be with this?
With silicon in the batteries, we should be able to store, well, we'd be able to double. So weight per weight, silicon stores 10 times as much as graphite. But actually, if you put it into a battery and you take the weight of the full battery, that's more like double the capacity of a normal cell without any silicon in it. So yeah.
The cathode has to match the anode, right? Is that true?
That's right, yeah. So that's why you have to have, well, if the cathode only stores 1/10 of the silicon, then you need 10 times the cathode. So the cathode will weigh more and you need less anode.
Oh,
so
that's doubles.
So you can balance it. But when you take into account the amount of lithium that goes in, it gets, it gets a bit more finicky. Trying to make the cell store 10 times is not going to be possible, but double the capacity is definitely reachable. Yeah.
That's pretty promising.
Yeah, so you put silicon in there, but then the thing is, every time you put lithium in a battery, that's why your cells never last forever. Your batteries will always die at some point, because lithium gets consumed by these side reactions. So when it gets consumed by the side reactions, you have less lithium left, and lithium is the limiting factor in there. So it doesn't matter how much you can store in your cathode or your anode, the lithium will run out eventually. So when we try and balance that, put a bit more lithium in it without making it cost too much, then you end up with about double the capacity.
Oh, I see.
Which is a big step change.
Use the 10 times just to get more lithium in the battery, just to pack more in.
Yeah, we have to pack more. But then it's a case of the silicon always, when it first cycles, will always get consumed by the silicon. The lithium will get consumed by the silicon, but it's irreversible. So the lithium gets trapped, and you store it in these SEI layers, solid electrolyte interface, and that doesn't give you any charge anymore. So you have to waste lithium anyway before the silicon becomes stable and actually gives you back the lithium. But yeah, I guess I'll go through the basics of a battery, and then we can talk about silicon towards the end.
Yeah, so Max, BS chemical engineering, and then so in England they do like a 3-year BS degree, and then if you're like a top student in the class, then you do 2 years for 1 or 2.
1 year for the MEng degree. Yeah.
Ends up being like 4 years. They don't do co-op or anything, right? You don't, or do you mandatory work in a company or something?
You can do. I didn't, because I wanted to do research. But yeah, there were a lot of people in my year who went into industry for an extra year. I went to Buffalo on a year abroad, so that was my co-op essentially.
Yeah, these guys all they do 5 years and they do a co-op.
Yeah.
So basically, you're a student for 5
cool.
years.
Okay, cool. Yeah.
Masters at the same time. I think it's like another year or something. But,
cool. Okay. Yeah. Should I share my screen then and get going?
Yeah. So you can do it, right?
Yeah. Yeah. Let's see. Oh, and that was just there.
Should be the green.
Yeah, here we go. Got it. Yeah, the screen disappeared. Okay. Can you see that?
Yeah. And that's it. Let me
just put it onto. Cool. Okay. Yeah, should I start then?
Yeah, that's good.
Cool. So yeah, a bit about me. I guess Professor Beaucage already gave me a very nice intro. But in short, I did a master's in chemical engineering. So I guess I'm in the same shoes. I was in the same shoes as you guys are now, maybe 6-7 years ago. And then I did a PhD in the same university, same department, and it was on energy storage and its applications. But I did it with Professor Siddharth Patwardhan, and I made silicon anodes for lithium-ion batteries. So I took silica, it could be anything, sand, glass, something like a raw material, and then you convert that straight into silicon using magnesium. And then when I finished that, I went and did a postdoc at Dalhousie University for a year. And I carried on doing reductions of silica there with a professor called Mita Dasog. And she was really well known. She is really well known in the magnesium reduction field. That's why I went to work with her. And now I'm still making silicon anodes at Ionic Mineral Technologies. So I've been here for about a month now. I'm in Utah, kind of south of Salt Lake City in Provo. Yeah, so given that I've done a lot in batteries and silicon, I am going to give you a talk about how we size up batteries. And so you might not be familiar with the terminologies and how you do the calculations for it, but I'm going to go through it and I'll show you that it's fairly straightforward. There's no fancy calculations. And from here, you should be able to work out how much, if you wanted to use a battery for an application, how big the battery needs to be, how many batteries you need, what type of batteries you should choose. So let's start off with the terminology and the calculations. I think we're all familiar with voltage, current. We should be familiar with parallel and series circuits. And then we're going to talk about capacity and energy, but the units I'm going to use here, just to be clear, are amp hours for capacity and watt hours for energy. And then I'll talk about the C rate, which is how quickly you can charge a battery. So firstly, I gather you're all chemical engineering students. This helps me keep in mind of how voltage and current relates to chemical engineering. So voltage is like the pressure that you're using to push your electrons. Everything that you use, the wires that you use, the metal, right? The metal used in your wires, they have electrons in them, right? But you have to get them to flow in order to produce a current. So the voltage is the thing that pushes the electrons. And then the current is the amount of electrons that flow per second. So you multiply these two, you get power in the same way that you multiply pressure and flow rate, you get power in chemical engineering terms. So when you're dealing with a fluid. So in a series circuit, this is probably a refresher for most of you guys rather than the first course. In a series circuit, you put voltage together. Let's say you have some source, so like a battery, for example, 1.2 volts. You put them in series, you end up at 3.6 volts. You add the voltages together. Whereas now if you put them in parallel, so now the electrons can flow different ways to the to your resistor or whatever you're powering. Now it can flow through 3 different ways. You add the current up. So the current adds up, but the voltage does not. So you still have a 1.2 volt circuit, but it's 0.3 amps. You can put more current through it. So this is important because batteries have a maximum safe operating voltage and current. For lithium ions, you have a nominal voltage of about 3.6 volts. So when you start off, it's going to be fully charged, let's say 4.2 volts. When it goes down, it's going to be around 3 volts or just above that. So you nominate 3.6 volts as an average voltage. So if you, sorry?
Like the rate, like if you have a car battery and it's like the rate.
Yeah. Sorry,
You
cut out there. What was that? Sorry.
Or how fast you can charge your car, you know?
Yeah. Yeah. So the more cells you have in series, the more current you can put through it. So rather than have current flowing through one cell and then the next cell, you can put current through multiple cells. So you can actually increase the charging. That's what I mean. That's why it's better to have loads of cells to make one big battery rather than one massive single battery.
The heat it generates is going to be like I squared V, right?
Yes, yeah, that can't be avoided. So the current that you put through is going to be going to generate heat. Yeah. But I mean, I'll get into that in a minute because you make different cell configurations. So you got pouch cells, cylindrical cells, coin cells, and they have different, some give you more energy density, but have a poorer heat dissipation characteristic. But I'll talk about that in a minute. So you can see how each single lithium-ion cell is 3.6 volts. How are you going to power a car that way? Well, you have to put them in series and parallel so that you can have enough voltage and current to push a car. So this is fairly important to keep in mind. Okay, so let's quickly talk about capacity. We have a fundamental unit, charge, which is measured in coulombs, and we've got current, which is measured in coulombs per second, right? And we have to put a time in there. So you divide charge by time, you get a current. How many electrons essentially you get per second. So the capacity of a battery is usually quoted in amp hours, right? Now, if you think about it, capacity is just charge. Current is charge per time, right? So I is equal to C over T, whereas capacity, you see here, is amp current multiplied by hours, which is time. But what's current? Current is charge per time, right? So if you multiply this out, time multiplied by time gives you coulomb. So essentially, what I'm saying is capacity is just a coulomb. It's how many electrons you have. So it's easier to quote in amp hours because you can say 1 amp hour capacity can supply a current of 1 amp for 1 hour. So it's easier to quote it in this way for the general public, and also to say how long a battery can supply for, rather than have to calculate your charge and divide it by the amount of time. Okay, capacity versus energy. There's a big difference here, and these can be interchanged a lot in the literature, but you've got to be aware that there's a big difference. So capacity is just the amount of electrons. I've just gone through that, and the amount of electrons you have in your battery or in whatever energy storage material. But that doesn't tell you how much energy, right? That's just the capacity. So for example, if I had it on the left side here, let's see. Here I've got some sort of bucket of water or container of water, right? But I can't use that to generate energy. I have to put energy in there to move this water to a higher bucket. This is ground level, right? So there's no usable energy. I've got the capacity, I've got the water in there. In the same way in a battery, I've got the electrons in there, but they don't have the energy. Whereas here, I've got a positive voltage, I've got pressure. If I run a pipe from this bucket to this lower bucket, water is going to flow and it'll give me energy. So the capacity is how much water or how many electrons you have, but it doesn't tell you how much energy the electrons can give you. That needs a voltage as well. So here's where energy comes in. We've got voltage and current. We know capacity is quoted in amp hours. We've got time. And we're aware of a unit called power, and we've got energy content. So the literature talks about energy content in watt hours. You'll see, a car can store so many watt hours, or however many watt hours you use in terms of electricity for your energy bill. You put these two together, capacity and voltage, and you should get energy content. So these two, I'm trying to show you the difference here. You need voltage and capacity together. So how do we derive that? Well, we've got power is energy per time, right? You rearrange that, you get energy is power multiplied by time, but power is also voltage multiplied by current. So if we substitute VI into this equation here, you see energy is voltage multiplied by current multiplied by time. So we've already seen that current multiplied by time, or amp hours, is capacity, right? So all you do is you substitute IT for capacity, amp hours, and then you multiply that with voltage. So that means if I give you a battery, I need to tell you the voltage of the battery and the capacity of the battery. And from there, you can work out the energy content in watt hours. So this is where energy is now given. It's not in joules in this case. You can convert it to joules, but here it's important to know that in the literature, watt hours is used, and this is where this unit comes from. Okay, now we've got that, we can talk about C rate. So the C rate is the rate of charging or discharging of a battery, quoted as multiple of capacity of a battery. So what does this mean? If I took a 3 amp hour battery, okay, if I charge that at 1C, right, C rate stated as 1C, then it will take 1 hour. So 1C will take 1 hour to charge. If I half that C rate, it will take twice as much time to charge, 2 hours, right? So in order to charge 3 amp hours in 1 hour, I need to supply 3 amps for 1 hour. So it's now that we have capacity in amp hour, right? C rate given in multiples of the capacity, it's easy to see then how long it takes to charge a battery. So 0.1C, I'm giving a 1/10 of the current, but I need to supply it for 10 times the amount of time. So 10 hours. So this is where C-rate makes it easy to work out how long it will take to charge a battery. And this is also something that's quoted in literature a lot. So if you do read the literature on the, or you want to find out more about batteries, that's what C-rate means. Okay, so I should have taken this away, but anyway, let's take a very British example. How much energy will it take to boil the kettle then? So let's say a kettle is 2 kilowatts, right? It takes approximately 45 seconds to boil 1 cup of water for tea, right? So 2 kilowatts, let's say it's a steady 2 kilowatts, it runs at that power for 45 seconds. It gives me 90 kilojoules. Then I just divide this by 3,600 because I want it in hours, right? And this gives me 25 watt hours. So how much energy is this relevant to how many times you can charge your phone? Well, if I have, let's say, a Samsung Galaxy and it's 3,000 milliamp hours, this is going to be the same for most phones around this generation. You get so it's 3,000 milliamp hours or 3 amp hours. The charger is capable of supplying about 2 amps. Let's say I charge for approximately 2 hours. You plug it in, sometimes it tells you how long it's going to take to fully charge from 0 to 100%. So 2 hours means half C. I don't even need to know how much current's going through because 1 hour is 1 C, 2 hours is half C. The voltage is 5 volts. So the energy consumed is 1.5 amps. Now, because it's 3 amp hours, the current I'm supplying is 1.5 amps for 2 hours, right? So 2 times 1.5 gives me the 3 amp hour. Multiplied by the voltage, that gives me watt hours, 15 watt hours or 54 kilojoules. So this is equivalent. Boiling your kettle once in 45 seconds uses as much energy as charging your phone 1.5 times. So this is how you can very easily convert. You can work out how much energy is required to do a certain thing compared to how much energy is required to charge a common electronic device. Okay, so this is how you can use the equations and all the terminology we've just looked through in some way practical. So comparing, now that we know what watt hour is, we can compare. This is a Ragone plot, and this shows you how much power and how much energy a certain energy storage device can provide. So power is how much energy it gives you per time, immediately, how much energy I can draw. Energy is how much, obviously, energy I can get from the storage device, completely. So we want something so let's say we want to accelerate a car, right? Accelerating a car takes a lot of energy instantly. So you want a high power, it takes a lot of power. Whereas if you want to drive the car for a very long distance, you might not need such a high power, but you need more energy. The more energy you have, the further your car will travel. So really, we want to be ideally up in this top right corner. But then you can see here, there are devices all across the range, but nothing in the top right corner. We can only choose either between high power or high energy, usually not both. But lithium ion, this is why lithium ion is so special. It can supply fairly high power and also stores a fairly high amount of energy compared to, let's say, nickel cadmium cells, which are common for remote controls, and AA cells, lead acid, which is what you see in your car. And also you might have heard of a fuel cell and a capacitor. So fuel cells technically isn't an energy storage device, it's a conversion device. You put fuel through it and it converts it into electricity. So technically this shouldn't be here, but the energy density is really here. What it's saying is this is the energy density of the fuel you would use in a fuel cell. So hydrogen, for example. A capacitor, this is very common in it's pretty much in every electronic device. This capacitor can discharge and charge very quickly, almost instantaneously, but it loses all its charge almost straight away. So it's not very good. It's good for powering things very quickly or absorbing a spike in current to protect the circuit, but it's not very good at supplying energy over a long period of time. That's why lithium-ion batteries, this is how it compares to everything else, and that's why it's chosen for electronic mobility applications. So looking at lithium-ion batteries, there are different types of lithium-ion batteries. So there's the polymer electrolyte lithium-ion battery, there's lithium metal, loads of others that are not on here. There's also the lead acid battery. You can see this is not lithium, obviously, technology, but to compare, you can see the energy density. This is now watt-hours per liter and watt-hours per kilogram. So this is volume and this is weight. So the higher up it is on the x-axis, on the y-axis, the smaller physical space it takes. And the further along towards the right on the x-axis, the lighter the battery. So you can see it's much more energy dense than lead acid. This nickel cadmium, nickel metal hydride, these two here are what you find in your AA cells or AAA cells. So this is why lithium ions are so important. Other common battery types. So now that I've introduced you to a few and why lithium ions are so great, I'm going to talk about, I'm going to give some credit to the other battery types. So let's talk about them. Just a useful note, when I talk about these cells, I'm talking about electrons flowing from the anode to the cathode. So negative electrode to the positive electrode. This is when it's supplying energy. So I'm using the cell. Electrons are going from the negative to the positive electrode. However, in electronic circuits, you might be aware that current conventionally flows from positive terminal to negative. What's actually happening is the electrons are flowing from negative to positive. But this is just convention. In batteries, during charge, you store energy in the anode. So regardless of what convention you're using, electrons are stored in the anode. That is the negative electrode. And when you discharge it, it goes into the positive electrode. That's the cathode. And all chemical reactions written here, half or full, are written so that forward reactions are spontaneous. So these forward reactions are happening when I'm using my cell, not charging it when I'm using it and discharging the cell. So this is just to be clear for the coming slides. Okay, so this is a refresher. You might have already seen this. This is reduction. These are reduction reactions and the voltage for each one. So spontaneous reactions are determined from, so if you couple these reactions together, it tells you which way your reactions are going to go. The more positive the potential, so if I take fluorine going to fluoride ions, the more likely it will accept electrons. So fluoride ions are very capable. They are a reducing agent. An oxidizing agent. They pull electrons very easily to fill their outer shell. So the more positive, the more likely it accepts electrons, the more oxidative it is. And the lithium is at the bottom here. It's a very reducing material. Okay, so this is something that's very common, still being used now, nickel metal hydride batteries. They're essentially a hydrogen ion battery. What's happening is you get this metal, which is a mix. There's lanthanum, there's all sorts of cerium, different alloys. And this is at the negative electrode. What happens is it gives the electron. So this is discharging, right? You have your hydroxide, aqueous ions. You've got the metal holding the hydrogens, the metal hydride. And what happens is it gives the hydrogen to the hydroxide ions, forms water, and you've got this metal solid. And it also loses an electron. Now this water shuttles across, right? And on the positive electrode, you've got this nickel oxyhydroxide solid electrode. The water then reacts with it, gives the hydrogen ion to the nickel oxyhydroxide, becomes nickel hydroxide, and also it gains the electron. So the hydrogen ion is going from the metal to nickel oxyhydroxide, and then back and forth. When it's charging, it goes back the other way. Right? The water essentially takes the hydrogen, gives it to the metal, and then discharge, the water takes the hydrogen, gives it back to nickel oxyhydroxide. And this is under alkaline environments, so hydroxide you can see here. And this is has a nominal voltage of 1.2 volts. This is very important because if I go back, you see when it gets here 0, this is the standard hydrogen electrode. If we go above that, so 1.23 should be around here somewhere. Yeah, here. Water at 1.23 volts will split into oxygen and hydrogen. So we cannot go above 1.23 volts. In reality, it's going to take more than 1.23 volts. It's probably going to be more like 1.3 or 1.4, depending on the material you use. But once you approach 1.2 volts, you start to split the water into hydrogen gas and oxygen gas, and that stops these reactions from working. That's why these cells only work at 1.2 volts. And it works under alkaline electrolyte. So this gives the conductivity, and also it means that the water can be split into hydroxide and form water again. So that's why these voltages are limited. Okay, lead acid battery. These are common in cars, are still used in cars, in combustion engine cars. What happens is at the negative plate, you've got lead and you've sulfuric acid, and this forms lead sulfate, giving away an electron and a hydrogen ion. So the electron goes obviously through the external circuit to the opposite electrode, or from negative to positive. And then the hydrogen ion shuttles across. So you have your, on the positive side, you also have sulfuric acid electrolyte because it's immersed in it. You've got this lead oxide and it gains the electrons, and what happens, you get lead sulfate. So the sulfuric acid reacts with the lead oxide, you get lead sulfate, and you also make water. So both sides, you make solid lead sulfate. This is why if you fully discharge your cell, you end up with lead sulfate. There's no more lead, there's no more lead oxide. But when you charge the cell, right, you can't, if you don't have lead there to begin with, you can't form lead onto it. So as you discharge your cell, lead becomes lead sulfate. When you charge your cell, lead sulfate becomes lead. But if there's no lead in the first place, the lead sulfate will not then spontaneously turn into lead again. So that's why there always has to be a small amount of lead and lead oxide on each side of the electrode. This is why you cannot fully discharge it's bad to fully discharge a lead acid battery. But one thing you can do, one thing that's so special here is that you can see it makes water. One of the byproducts is water. So that means your sulfuric acid becomes diluted. Sulfuric acid is very, very dense. You know, pure concentrated sulfuric acid is very dense. So you can measure the amount of charge that's left in your cell just by measuring the density of the fluid. So you can take, there's obviously not for the common lead acid batteries, but there are ones where you can take a little, you can open a port, take out the electrolytes and the electrolyte, and measure the density of it, and that tells you how much charge is left. So the more water you have, obviously the less concentrated the sulfuric acid, the less dense it will be, and therefore the lower the charge. And also if you overcharge, you can cause water splitting, because again, water is there. So you can measure the voltage, you can measure the amount of charge by voltage or by measuring the density of the electrolyte. So you might be wondering, why is it then that lead acid can be run at 12 volts? It can supply 12 volts, even though it splits water at 1.2 volts, right? In fact, each cell should have only 2 volts, but 2 volts is above the 1.2 volt threshold for splitting water. Well, lead is a very poor catalyst for splitting water. So there's a huge overpotential. You can go to above to up to 2 volts and still it will not split water. So the 1.23 volts is a thermodynamic minimum, but usually there's a lot of inefficiencies depending on what metals you use. So lead, you need 2 volts and it still won't split water. Any more than that, though, it will start to split water and you make hydrogen, and that's bad for the battery. So in here you have each cell, each pair of lead and lead oxide gives you 2 volts. So you have 6 of them in series to give you this 12 volts. And that's how you get 12 volts. So this is a battery with 6 cells, 6 lead acid cells in them. Okay, and the final one, this is one of my favorites, actually. It's such a simple technology. It's fairly cheap if you take into account of its cycles. So this nickel iron battery starts off where you have iron and a KOH or an aqueous hydroxide solution. And then this dissolves, giving away an electron that goes outside of your circuit or in the outer circuit, and then you have iron hydroxide. And then in the positive electrode, you have nickel oxyhydroxide, again, reacting with water, taking the electrons, forming nickel hydroxide, and then you produce this aqueous. So it's balanced. You take a hydroxide here, you produce a hydroxide here, and you make iron and iron hydroxide, and then here you make nickel hydroxide. It's only 1.4 volts, and it drops to 1.2 volts during discharge. So you only have a voltage here of 0.2 volts, but you can stack them up and build the voltage up in series. But they're really durable because you've got such a small window, there's not such a huge electrochemical, a varied electrochemical environment. It's only going up and down by 0.2 volts, which means you can cycle it many, many times, many more times than 30,000 cycles something go to. In comparison, a common lithium-ion battery should only be cycled, 1,000 or thousands of times, not tens of thousands of times. So this is something that's obviously very heavy, low voltage, low energy density. But if you have space, for example, to store energy in your house, you can buy a bunch of these, stick them in, in the garage or something, in the shed, and you can store energy for many, many years. You don't have to replace them as long as you keep, get a battery control system to stop it from going above 1.4 or below 1.2. And you can store a lot of energy for a long, long time. It's a very, very simple. And I guess every so often you have to open it and top it up with electrolyte. So water might come out. So you just top it with water, measure the pH. If you need to put KOH in there, you put KOH in there, bring the pH back down. But yeah, this is a very simple technology. Iron and iron oxide, it works in water, so you don't need to build it under an atmosphere. And these are common ingredients you can find. So yeah, very useful battery, has its applications. And then finally, obviously, this leads up to lithium-ion battery. This is the most widely known, the most commonly used at the moment, the most technologically advanced. How a lithium-ion battery works, you might be aware of this already, but just to make sure everyone's on the same page, the anode, common negative electrode, is graphite. Because of its layers in between, you can store lithium ions. So when you charge up the battery, lithium ions move into the graphite. And when you discharge it, they move out of the graphite and into some other cathode material. And this can be a layered structure or can just be kind of a mixed metal structure. And the lithium ions just shuttle back and forth, basically. One has a higher voltage than the other. That's why when you discharge it, lithium ions will want to move spontaneously and it produces electricity. But the problem is that lithium is highly reactive. So it requires the absence of water or oxygen because you make lithium hydroxide or lithium oxide, and this can produce hydrogen as well. So it's fairly difficult to make. You need specialized facilities to make them. So calculating the specific capacity, using what we've gone through with the capacity of the cell, how we calculate this is you have to first come up with your reaction. And you need to know what reaction this is, and this will be reported in the literature and textbooks. So 6 carbons will store 1 lithium. It's kind of a hexagonal shaped carbon. It stores 1 lithium and 1 electron. So how much energy will 1 gram of carbon, because it's per gram, how much will 1 gram of carbon store? Well, we convert this to moles, right? And the total capacity here is calculated by the charge on the lithium ion, which is 1. So for every 1 lithium ion, you get 1 electron. The moles of lithium multiplied by the Avogadro's number, and then this is the elementary charge of electron. So if we have the moles of carbon, right, you multiply that, you divide that by 6, and that gives you the moles of lithium. And then that's your moles of lithium there. You've got Avogadro's constant. So that gives you the number of atoms of lithium. And then the charge of an electron is the charge per 1 electron. So 1 lithium gives you 1 electron, and then 1 electron gives you a certain charge. You multiply all these together, you get your milliamp hours, and then that's per 1. Because you started off 1 gram as your mass of carbon, you get milliamp hours per gram. So this is the equation you need to use to check how much capacity your material will produce, given this equation here. Now, it'd be a different story if this was 7 carbon or 8 carbons. This number would be less, obviously. And if it can store more lithium, it's going to be more. So this is how we calculate milliamp hours per gram of lithium, of capacity of carbon. Okay, so here's a simple application of this calculation. What is the minimum amount of lithium in your smartphone? So let's use, again, 3000 milliamp hours, or 3 amp hours, right? This amp hours can be converted. This is a charge, right? Converted into coulombs. So you multiply that by 3,600, you get 10,800 coulombs. And then each electron has a certain amount of coulombs. So you can convert that, and the charge on 1 electron is 1.602 times 10 to the minus 19, right? You can then work out how many electrons you have, right? And this means that if you have this many electrons, 6.7 times 10 to 22, then you have 6.7 times 10 to 22 lithium ions, because one lithium gives you one electron. Now this you can convert, this is number of atoms of lithium. Use Avogadro's number to convert that back into moles of lithium. Now you have moles of lithium multiplied by its mass or its molar mass. You now have the grams of lithium. So in a battery for a smartphone with 3000 milliamp hours, you need at least 0.77 grams of lithium. This is at least, because when you add more than that, if you add less than that, you'll never reach that. But also when you add exactly 0.7 grams, some of it will react, as I said, in side parasitic reactions. So you always need extra to be able to remove, to be able to account for that loss. So you always have this 3000 milliamp hour. This is to begin with, but obviously over time it's going to decay. So just about a gram of lithium is what you would need, but probably more than that. But this is the minimum. This is how you can calculate based on the capacity. Okay. How are lithium ion cells built? You're probably familiar with most of these. So there's the cylindrical cell. This is the most efficient or the most energy dense, because what they do is they stack, or they have these sheets of cathode, separator, anode, and then obviously the stainless steel can it's in. You have the separator, anode, and cathode laid on top of each other, and then they kind of roll up. So they roll up into this jelly roll, and then they slot into this can. This is actually very difficult to do, but by doing this, you can wind it up really tightly, so you can shove it into a very, very small canister, which means now you have a smaller cell with the same amount of energy. And we've got this prismatic cell. Now, I don't know if you're all old enough to know, but all the older phones, mobile phones, are not smartphones, like the brick kind of Samsung phones. If you take the back off and you see these kind of flat cells, or actually some cameras might still have them now, they're kind of flat rectangular cells with rounded edges. These are prismatic cells. These are also pretty efficient because you can wind them really tightly. But the benefit of this is that it's now got a higher surface area. So you've got the flat side on the top and the bottom, and that helps you dissipate heat better. You might be aware of the pouch cells. Pouch cells are used in some cars. The Nissan Leaf uses pouch cells. These are great because you can have, well, each single cell stores more energy than a cylindrical cell. But these cells are really, really flat. So they just literally lay the electrode, separator, and the other electrode on top of each other, and then seal them. And then you have the tabs on the end here at the top where you can, that's the positive and the negative. So these cells are so flat that if they produce any heat, you can blow away the heat. So the high surface area makes it easy to cool these cells down compared to the cylindrical cells. If you imagine the cylindrical cells, as you wind them, the layers stack on top of each other. So when the heat's produced at the center, it has to go through all these layers to dissipate out. And then there's the humble coin cell. These you have also probably seen in some older watches or some smaller devices that you have at home. These are commonly used in academia, and you have the positive and the negative case here, and then you've got the positive and negative electrode, the spring, just the kind of pushing heat tension, and then you've got a separator to stop the two electrodes from just discharging across each other. These coin cells are really easy to make, really reproducible. Once you learn how to make them in the lab, if you want to go into research, these are really easy to make, and you can very quickly test. You don't need so much material. You only need a small amount of material, and it's easy to make, it's cheap. That's why they use in academia. If you're making 100 different materials and you want to test them all and see which ones are good, then you want to be able to make them really quickly, really easily. These other cells are more commercial applications. They're not for testing, they're more for actually using. So the first three are less commonly used in academia. There's a terminology here called 18650, and this is because this is used to call the, this is the name of the cylindrical cells. There are different names, there's 14500, but 18650 is common as well. These are used in the Tesla cars. Not anymore, they use the more common, the more modern one, which is 4650, I think, something like that, can't remember. They're called 18650 because they're 18 mil in diameter and 65 millimeters in height. And that's how you know they're 18650s. The AA batteries that are common, they're around 14500s, but they're not usually lithium ions. They're usually, nickel metal hydrides, 1.2 volts, 1.5 maybe. So these cells, the common ones that are used in automotives, you have the Tesla Model S. This is a bit outdated now, but you have the 18650s and they stack them. You have one cell and they stack them in a module, and then they have 6 cells per module, but 16 modules in series and 74 modules in parallel. And then if you work this out, each Tesla battery has 7,104 cells roughly. And then if putting these together, you get 360 volts. That's how you can have 3.6 volts on each cell, and you can have 360 volts in the battery pack itself. The Nissan Leaf uses a different technology, uses a pouch cell, and has 2 cells in series, 2 cells in parallel in one module. And so you've got 4 cells in the module, and you have 48 modules altogether. But each of these cells can store 32 amp hours per cell. Each of the 18650s in Tesla stores roughly 3,000 to 5,000 amp hours, I believe. So this is a much bigger battery and stores a lot more lithium, therefore you get a lot more capacity. But you have less cells, only 192 power cells in the Nissan, but you got 7,000 cells in the Tesla. So let's say they were both equal in capacity, which they are not. The Model S stores a lot more. You still need less cells, less power cells in the Nissan Leaf. But each have their own benefits. Like I said, the 18650 is wound tightly, takes up less space, whereas these are not really under pressure or anything, but have better cooling characteristics. You can blow air across them and it takes heat away very easily. These are harder to cool. Okay, so now we know what cells are being used, how you make a cell for lithium-ion batteries. We should talk about how they discharge. So they don't discharge straight, so they don't just keep giving, they don't hold a certain voltage and then drop. So, okay, let's talk about the capacity and the C rate. When you charge and discharge a cell, you know that battery degrades after many, many cycles. Eventually it dies, you have to replace the cell. If we use different C rates, different amounts of capacity will be stored. So for example, if I had, let's just take the blue dot here, just follow the blue dots, ignore the rest. The blue dot, if you charge it at 0.1 C, so 10 hours to charge, you store about 550 watt hours per kilogram. But if I start increasing those C rates, right? If I want to charge it quicker, I start to store less energy. So the quicker you charge a cell, and this is a kind of tension that you'll have. It's either high energy or high C rate. It's very difficult to get both. There are materials out there that can do it on their own, but it's difficult to get both. So you have to be aware that when you charge a cell really quickly, you tend to end up with less energy. Also, higher C rates, as Professor Beaucage pointed out, we have a high current and actually produces a lot of heat. This can damage and degrade the material. So higher current, while it saves you time, gives you less capacity and can also damage your battery. So we have also the discharge curve here. When you fully charge a cell, it has a high voltage, 4.2. And then as you discharge, you see the voltage isn't constant. It's actually dropping as you draw current from it. So this is why lithium ions usually have, or most cells have, their own kind of control mechanism or control device, so that it always feeds out a fixed voltage. It can convert 4 into 3.6, and it can boost up lower voltages up to 3.6. So that means your device sees a constant voltage as your cell is depleting. And you can see here, so after I think this was only 10 cycles, I believe, 6 cycles actually, 6 cycles. On the bottom right, you can see here, after 6 cycles, this is a fresh cell, the blue line, and after 6 cycles, it can store even less energy. So this is the discharge of the 6th cycle. You can see that the capacity that ends up here, once it's finished, is about 160, but it's just above that 165. So it's only 6 cycles, so it's degrading pretty quickly. And this is what it looks like when you discharge a cell. The discharge shape is dependent on the cathode material. The material, when I say the material, I mean its structure. So here you have a spinel and olivine structure. So these two here, these have robust, strong structures that do not distort when intercalating. So these are not layered structures. And so that's why when you discharge the cell, it holds the voltage, the structure doesn't change. Whereas for the layered structures, they distort during intercalation. So when you charge the cell, it pushes up the layers, or the layers get pushed further apart to force these lithium ions in. as you discharge the cell into, so this is the cathode, right? That means as you discharge the cell, you're pushing lithium ions into the cathode. So it's coming into these layers. But some of that energy is being put into pushing these layers apart, which is why the voltage drops. So this voltage doesn't stay. As you push more lithium ions into it, you force the layers apart, and the energy is being used to push the layers apart. Some of it is being used to push the layers apart. That's why you get this voltage drop. The spinel and the olivine structures do not change in structure. So they have a straight discharge curve, and then they drop off. But that also means that you can store a bit more energy with the layer structures. You can kind of force more lithium into it if you need to push the layers apart, and it ends up storing more capacity. Okay, and this is the final part now. Silicon anodes is what I work on. So there are many different anode materials you can use. The most common, as I've said, is graphite. Graphite is an intercalation anode. So it can actually, it's got the layers and the lithium ions going between the layers, and that's why it's intercalation. There are other materials, so that you can get conversion anodes, which react with the lithium, doesn't hold its structure. The anode doesn't actually hold its structure anymore. It forms a new structure, or either a crystalline or an amorphous structure with the lithium. So these are conversion anodes. And you can see conversion anodes store a lot more energy than intercalation anodes. So that's why there's a break in the curve here at 1,000. So this is orders of magnitude. So naturally, if you had to choose a material, you'd want to choose something with a high capacity, right? This is the potential as well. So for an anode, it's good to point out you want the voltage to be very low, and for the cathode, you want the voltage to be very high. It's the difference between the cathode and the anode that gives you the voltage of the battery, right? So you want them to be very far apart. If you have the anode and the cathode at the same voltage, right, there's no way for electrons to move from one side to the other. Both sides are at the same voltage. There's no pressure difference. So conversion anodes look promising. They're down here, low voltage, very low voltage, and high capacity. So looking at the conversion anodes, right, we're zooming in now here. So on the right side here, we've got silicon, germanium, aluminum. These are metals that can be used as anodes. Lithium, pure lithium is up here. That could be used as an anode as well. Very, very high capacity. Graphite is down here somewhere, 375. So you can see there's a stark difference. So looking at these alloys, right? This alloy region has the lowest voltage compared to all these other anodes, right? But it's also got a very high capacity. So that's why we want to look at silicon. So let's look at silicon. I'm going to tell you about the reaction is 4 silicon atoms reacting with 15 lithium. So every 4 reacts with 15. So it's roughly 4 lithiums per 1 silicon. In contrast to carbon, where you need 6 carbons to store 1 lithium. Here you've got more lithium per silicon. And we go through the calculation again. How much energy can 1 gram of silicon store? So this is the equation that I've shown you before. We have the number of, so here 4 silicon gives you 15 lithiums. That means 4 silicon gives you 15 electrons. This should have a 15 in front of it, sorry. And if you do the calculation with the charge of the electron, number of lithium ions, number of electrons, you get 3,571 milliamp hours per gram. In contrast, graphite has 371. So it's nearly 10 times the capacity. This is why silicon is so important. You can swap the graphite out for silicon. You can massively, take out 1 gram of graphite and use 1 gram of silicon. You can massively store a huge amount more of lithium and capacity. The problem with silicon, as great of a material as it is, it's got very high capacity, but it's got low cyclability. So when you charge it, it's an alloying material. It alloys, but it's an amorphous alloy. It alloys with lithium. So this structure, there's no structure. This Li15Si4, there's no structure. It just forms an alloy. And this alloy just cracks. It expands 300%. So the volume expansion causes it to crack. So silicon, very high capacity compared to all the others. So aluminium, germanium, tin, and antimony. These are the other alloying materials. Carbon's graphite, which is down here. Silicon is so much higher, but it cracks, right? So when you charge it, it expands, and then it exfoliates. So when these individual chunks of silicon don't touch each other, they're not electronically conductive. So they just sit in the battery. They're not touching the rest of the electrodes. and they don't, you can't get electrons to them. They can't give electrons either. So they're stuck in the middle and they're not storing or giving charge. So that's why it degrades so quickly. If you make it porous, right, then what happens is it has pores in its own structure to expand into. The mechanical stress isn't so high. So now it doesn't crack and you can charge and discharge for many cycles. Making silicon is a challenge though. How you would go about it is you start with silica and you can go through the metallurgical grade silicon process. So you do this by the carbothermal reduction, 2000 degrees Celsius, and then you can further refine it and make silicon, but that still isn't porous, right? This, you then have to go, you don't have to etch this silicon in HF to produce pores in it. Whereas if you use the magnesiothermic reduction, right, you get silica going straight into silicon, and this is at 600 to 800 degrees Celsius using magnesium, and you get porous silicon straight away. So actually, this isn't just silicon that should be down here somewhere, it's a porous silicon. So the magnesiothermic reduction, how it works is you get silica and magnesium, mix them in the powder. This is what it looks like in the lab. Mortar and pestle usually is what is used. You put this in a stainless steel crucible, and you stick it into a furnace. The furnace, now magnesium really wants to react with oxygen, so we have to keep oxygen out by flowing argon through it. So we seal the furnace and put flowing argon through. We then heat it up to roughly 650 degrees Celsius, right? And this is held at this temperature for around 6 hours usually. And we cool it down, we take it out, we put it into this either hydrochloric acid or sulfuric acid. 1 molar is enough, you don't need anything too concentrated. This gets rid of the chlorides. It gets rid of the magnesium in there because we put magnesium in the first place. All the magnesium gets turned to magnesium chloride. Now all we have left is silicon, and this is porous silicon here. So it's a very simple process. You mix magnesium and silica, you heat it up, you wash away the magnesium, and you got your porous silicon. Pretty straightforward. Problem is that it's quite expensive. Having done the calculations for the energy cost and everything, 6 hours at 650 is a pretty expensive, energy intensive process. So a lot of my work was looking at how to decrease this, decrease the cost of the magnesiothermic reduction process, which I'll talk about in a second. So this is what it actually looks like when you take the mixture out of the furnace. You see this brown kind of powder, and this is before you even wash it in acid. And when you wash it in acid, you get an even browner color. It's like a lighter brown. Then you filter this. So you wash it, you filter it, you get this kind of paste. How you put this into a battery, I'll talk about in a second. But the drawbacks of the magnesiothermic reduction process is that you don't have pore control. So it's presently not scalable and you don't have pore control. The pore control means that you heat it up to 650, the reaction is very exothermic. It kind of destroys your structure. So any kind of pore structures you have gets destroyed. Because it's so high temperature, it's not scalable because the production and also that makes the production unsustainable. You have to use a lot of magnesium and a lot of energy just to produce this thing to the silicon, which stores energy so that we can move away from fossil fuels. So you use a lot of energy in the first place to then save energy, which doesn't really make sense. So we need to make this more economical. There are ways to do this thermal control. So you can use lower temperatures and also you can limit the pore damage. You can use salt as a thermal sink. So you add salt to the mixture, and when the reaction happens, it absorbs this heat. And you can do this kind of two-step reduction as well. So you use low ramp rates and low temperatures. So you can go, 650, but you can stay there for 15 minutes, and then you can go down to either 100, 200, 300, or 400 degrees Celsius and remain at this lower temperature for 6 hours. So what happens is you get the reaction to start off at around 650. It produces its own heat and fuels the reactions. You then can switch the furnace off or bring it back down to 400 or 300. And then this now lower temperature kind of keeps feeding heat while most of the heat is coming from the reaction itself. So in this way, you can save energy. You don't need 6 hours. You can do 15 minutes. By adding salt, right? So the two things, the exothermic heat release and the heat from the furnace, these are the two problems, right? The heat released from the reaction damages the pores. It's so hot and it's really quick. It just happens straight away. What we can do is add salt as a heat sink. So this kind of absorbs the heat. The salt melts because this melts at around, sodium chloride melts around 800 degrees Celsius. then absorbs the heat, melts, and it can kind of feed that heat back into the reaction. And then you don't have to hold that 650 and keep feeding heat. So these are multiple ways of using thermal control. You can also use a eutectic reaction. So the reaction can proceed at 450 degrees Celsius. So you form this eutectic at 650, you melt the magnesium and the aluminium together, right? So this eutectic now, magnesium melts at 650, aluminium melts at 660. You melt them together and form this mixture with a specific ratio. And now once you form this eutectic mixture, it actually stays a liquid until 450 degrees Celsius. You don't have to go to 650. And then what happens is now you've got your magnesium in the liquid phase at 450. So this was actually carried out by the group I was working with in Dalhousie University at a specific ratio, right? You can have the reaction proceed at 450 degrees Celsius and you produce a very high yield of silicon, almost 70%, which is pretty good for 450 degrees Celsius. There's a way that a method I came up with. If you make your silica small enough, the silica feedstock, so I use Sturba silica, which is a sol gel made silica. What happens is you make small silica and the silica reacts. It's really reactive at small when it's a really small size. So here I've made 20 nanometer silica. And what I found was that if I heat it up, obviously 650 here, this is an XRD pattern. These peaks indicate there's silicon, right? Now, if I go to 750, I get silicon. 650, I still get silicon. 550, I still get silicon. And even at 450, usually at 450, you don't get any more silicon. You don't see any peaks anymore. But in this case, with 20 nanometer silica, you do. How much silicon do I get from it? Well, if I look here on the left side, on the left graph, if I use 500 nanometer silica, I don't actually make any silicon at 450. 75 nanometers isn't small enough either. 20 nanometers, and I've tried 25 as well, 25 and 30. 20 is kind of the sweet spot. You go below that and you can make more silicon. So here at 450, I can make a yield of 40%. Still not great, but it's better than nothing. Then I tried fume silica. This is 7 nanometer silica. And what I found was actually the silicon that you make goes up. And I've kind of worked out why this is now, but it took a bit of time. But basically, 7 nanometer silica is very, very reactive. At 450, you can make 40%, but you keep going down in temperature and the yield goes up around 60%. Whereas on the 20 nanometer silica, it actually just goes down to zero. Nothing happens anymore below 400. So the particle size, the smaller the particle size, the lower the onset of the reaction. So this is another way you can save energy, bring it down to use a smaller silica size, and you can bring the temperature down and still get a pretty decent yield of silicon. Okay, so how do we put the silicon to a coin cell? Well, just a few slides back, should have put this closer to that slide. This silicon you can see here, take it out, and you basically turn this into this kind of coating. You've got these are sheets of metal. So on the cathode side, you have aluminium sheet. On the anode side, you've got copper sheets. And you basically coat this anode onto the sheets. And what happens is you put the current collector, you have to have a current collector. So silicon will react with lithium. The lithium gives off the electrons, and the electron has to be carried to the sheet. So here we've got a copper sheet. So to make your anode, put the silicon into a cell, you have to have a binder to hold the powder together, and you have to have a conductive additive. So you have carbon black. And then obviously the active material, which is the thing that's storing energy, is the silicon. This is what it looks like here. So this silicon, you dry it out, mix it with carbon, water, and binder, just looks like a black ink, kind of a thick paste. It's like honey consistency. So here we have silicon, water, carbon, and then the binder I used was carboxymethyl cellulose, quite commonly used. It's soluble in water, and it's used in the food industry. It's fairly safe. And then there's obviously any unreacted silica that stays in the mixture. Then what you do is you drag this, you put this paste onto, here I've got copper foil, and you have this thing called a Doppler plate, and it spreads the ink evenly, so you get an even thickness across the sheet. Then with the sheet, you punch out individual kind of circular discs, right? And then we put this into a coin cell. So here we've got the lithium foil electrode, and that's where the lithium's coming from. That's also the electrode the other electrodes. You've got silicon here, which is your one electrode, and then you've got the lithium, which is the other electrode. Then you punch them into coin cells. And this is really the final slide I want to show you. So this is the full cycle now. You get the silicon, you make it from sand or whatever quartz, and then you put it into a cell, and this is what you get. So you charge and discharge. These are the discharge cycles, because when you charge, the charge is slightly higher, but really you want to measure the amount of energy that comes out of the cell, not the energy you put into the cell. It's going to be different each time. You always put in more energy than you get out of it because of the inefficiency of the battery. And so with different, you can see with different silicon that I've made, with the 20 nanometer particles, I store a very low amount of energy because the yield is very low. Same for this, and for the 650 Celsius reaction, it kind of degrades. It degrades slowly as well, which is fine. But then now I can make the same material with fume silica, 7 nanometers at 380. So the material, the red one, is material I've made with 650 degrees Celsius, and the blue one is material I've made with 380 degrees Celsius temperature. And you can see it roughly traces the same line. So although the cell isn't great, I said to you, silicon can store 3000, and this is only around 500. It's still more than graphite, which is 375, but also it's a step forward because now I've got the same material, but I made it at a lower temperature. So the inefficiencies come from the SCI formation. This is solid electrolyte interface. And this interface consumes lithium, and it's kind of like gunk that stays in there that locks up lithium. When you charge or discharge, the lithium stays in there, doesn't move anywhere, so it's permanent in the cell, and you've lost lithium, so you've lost capacity. And this electrolyte interface grows and grows. So if you use silicon and you expand it fully and it cracks, it forms more surface area, you then lose more lithium, forming more electrolyte interface. So that's why silicon's bad. But by making it porous and lowering the surface area, you can have a stable solid electrolyte interface, and you can have a very stable battery from it. This is kind of all I want to talk about today. I think I'm going to stop here, and I'll take questions, and if not, then we can call it a day.
Thanks, Max. It's pretty good. Do we have any questions or anything? We usually quit at 3.
Yeah, that's fine. I need to go in a second anyway. So I've left my email address here. So if you have any questions, you can just send it to me and I'll answer them. So,
web page, you're listed there, I think. So
yeah, on the website, if you go to Ion Mineral Technologies, then yeah, I'm there as well. So yeah, if you can't think of any questions now, you need time to digest. I'll share these slides with Professor Beaucage, and he can share them with you. There are some additional slides in there as well, which I didn't really want to go through because I didn't have time, but some stuff on moisture sensors and things, which Professor Beaucage really likes. But I'll share this with you, and you can take your own time to look through them, process, digest, and understand. And if you think of any questions, just send them to me. But otherwise, thank you for having me. Thank you for listening. This is I think it's my 5th or 6th year in a row now doing this, and it's always a pleasure doing it every year. Yes, so yeah, thanks. So thanks, Greg, for having me again. Yeah.
Thanks.
All right, I'll leave you guys to have a good afternoon, and I'll speak to you another time.
Okay, see you. Thanks.
That's it. Bye.